So my name is Totona. That's quite a name over there, but you can refer to me as well as Bruce. So I'm a faculty at Strathmore University, and my research, most of my research around for PhD studies is quantum machine learning. So I think for such wondering, I'm still within my PhD studies, not yet finished, but exploring quantum machine learning in healthcare IoT. So I'll just put it class general on quantum machine learning because that's the core with different application areas. So for this session, I would want to start with a very bit of a general question. So which will be, that's just an highlight. So perhaps how many of you have ever heard of the term quantum before this week? I understand there was at least one first seminar, one first webinar this week on the same program. So if you've heard maybe the term quantum computing before, just type 1 on the charts. And then if this is this week was the first time you heard of that term quantum computing, then type 2 on the charts. So at least just to know who we have here, and if the subject is at least quite new, or at least most of us are conversant. Okay, I'm quite excited, at least quite impressed that at least everyone have heard of the term quantum computing before, so which is really a good thing. So just a quick of a follow-up. If you've interacted with any quantum program before, or let me just use the term, if you've at least write or develop a quantum solution before, just type 1 on the charts. If you've not developed any quantum solution before, or just a quantum prototype before, just type 0 on the charts. So if you've developed quantum prototype before, just a 0, then no. So if you are yes for 1, and then no for 0. Okay, that's a good response. So at least this means if we call this bit of our quantum lesson number 1, basic of a cliche 101, then that's mean it's okay. So for this session, as it says there, demystifying quantum series. So for my case, I'd actually say extending to quantum things. So, but if you've written a program, I normally prefer use the term bit of machine learning, because for most of the guys I interact with, most of them are IT students, and in a way, they've always written at least, if not a new model, it's just a bit of the improvement of existing model for any machine learning algorithm. And so if you've actually written, then it's always just a good foundation. That's normally I tell individuals, it's just a basic, it's a good foundation. Because when normally we're discussing things to do with quantum, we have a place to start with, which is classical algorithm. So for example, if I say classical machine learning algorithm, just to throw some words around, if someone talks about quantum support vector, random forest, neural network, I hope something make sort of a sense. So for most of the cases, then we actually start there. because the cost of quantum computers are highly not really available, or mostly they're quite expensive. I think that's the term I'd actually use. So for example, if you go to a platform like, let me use IBM as kind of example, as we may have maybe representative from here. If you check some of the features you can actually get from quantum hardware, or even just the cost per time, you realize actually for the free tier is always 10 minutes per month. Otherwise, anything above that, of course, come with a cost. So the more the time, the cost, and the costs are not negligible. So what we've opted for most of the open source implementation, you find that it utilizes an hybrid of classical quantum environment. What I mean is, if you written machine learning, a bit of classification algorithm like TensorFlow, so you find environments which basically still utilizes the same. It's just that we use the quantum element on a software platform. So for example, PennyLane is purely a virtualized or simulated environment for the quantum hardware. So it's not really the tangible hardware, but it's a simulated environment. And for most of such algorithm, you'll find that there is a bit of the hybrid, classical, and quantum options. So anyway, so that is just the introduction here with my follow-up question of if you've written a quantum prototype. Prototype mean mostly just a basic of a prototype or actually a software. So nonetheless of that, so then with item number 2, from that basic mentioning of the machine learning. So when we're normally writing a machine learning, think of you trying to write a basic model. Let me know it as algorithm, a model to predict, let's say predict something on a climate thing, or just a basic of anomaly prediction, which basically you'd want a classification, which is, sorry, takes a binary state. Is it malign or not? Is it something malicious or non-malicious? So for most of the cases anyway, just in form of data, we work with the binary of 0 and 1, which we say the state is either 1 or a 0. And when we're transitioning from one state to the other, it's just from 0 to 1, 1 to 0. So where the quantum element of it come is basically a case. Normally, I just like using the term superposition. It's like apart from 0 and 1 states, then we're trying to say we can have a state which we can be in both 0 and 1, which then, of course, introduces something. Of course, then we talk about qubits. Just I think I don't have my charts can't say straight, so just in case okay, at some point maybe I'll just check in case there is any question, or in case it's something not I'm not clear or something, but in case I'm not clear. So for that 2 cases, so normally we start from that case, from classical bits to quantum bits. That's why we talk of classical machine learning, quantum machine learning, or basically classical algorithm. Classical is then the QNN option classification support vector machine. Then of course, then talk about the quantum computer, quantum kind of algorithm. Then of course, we'll actually talk in the case of entangle kind of a bits, which basically 0, 1, or a state whereby we are actually in both, which we're trying to say we can have a state which is both 1 and 0 for that kind of a case. So that is the quantum element of it, from the classical approaches to basically the quantum bit. It's, if I also report again in basic kind of a terms, if I'm explaining to someone doing communication or maybe someone doing a business course, it's just to say that for classical, we normally transition between 2 states, yes or no, on and off. However, with quantum bits, is like now we may have more than 2 states of 1 and 0, or on and off for this kind of a case. So to achieve that, or actually to explain that, we may actually use different kind of key terms. So at some point you hear someone talk about entanglement, superposition kind of things, or quantum parallelism. It's just to say with execution processing, the parallel element of actually more or several states at a time, which we may talk about speed later on. So anyways, those are just some key terms which I may want to define. But given that we're not teaching quantum, it's just that I'm trying to put into perspective of where we're picking from usual machine learning or classical algorithm, then to quantum algorithm. Two is, please, I may not define the basics of the quantum mechanics. There is something called basically what may define the hardware and other things. So for this case, I'm just speaking from more of a computing perspective. Otherwise, a physicist may actually then want to say, maybe a first to define this is basically the mechanics element of the quantum. So anyway, I've just picked from that computing element. So of course, there may be other terms. That's what I'm just trying to say. And for most of the cases, then where would we apply such kind of concept, quantum? So if you check, for example, online, or maybe from your interaction, you may have come across terms like post-quantum cryptography or quantum cryptography, which is basically different cryptographic algorithms which are based on quantum. Then other application areas, things to do with optimization. I've put there drug discovery as one of it, but there's quite a number of it. So is just using machine learning, you can do a bit of drug discovery. But if we want a very fast processing, for example, gene sequencing, then an option of a fast machine learning approach to that could be just quantum machine learning, just to make things very fast. Again, I'm just repeating, I'm not teaching quantum machine learning, I'm just trying to do a bit of introduction there. So also the terms, put it there. So do I need to define? I've just put it there. In the case, just to put a few things into perspective, as I said, superposition, which with Qiskit we talk of 1 and 0. So for this case, then we're talking about a situation whereby we have a state which can be both 1, 0, or are more states than 1 and 0. And then, of course, the entanglement, then which we bring in the aspect now of the qubits and actually several states simultaneously. And perhaps just the 3 terms are not enough. So there's quite a number of terms and you'll always come across if you join, for example, the quantum introduction classes. So do I need to define? Maybe not. So just trying to do a bit of the intro there. More importantly, is always a reflection. Why quantum computing? And mostly when we pose this thing, the first thing which come to the mind is the speed. So if I'm doing usual machine learning, it's actually okay. But if I need very fast classification, then that would mean then just the quantum element of it, which mean I bring in the parallel kind of execution or actually processing. And for that case, it's just to say maybe a CPU, GPU approach could be maybe slower than the quantum processing unit because of the quantum parallelism element. Is because with the CPU, we process 0 and 1, so which is quite slow, unlike when we can actually process several states simultaneously, apart from 1 and 0. So think of a circle, and within that circle, whereby instead of having 1 and 0 and 1, it could be just several states within a circle. So which means we can have several portions of the circle. And if those portions are actually the states, then it's just to say it could be actually more than 1 for that case. So I'll just use the case of maybe even 4 states and 2 states. So for binary 1, 0, 2 states. And then if we add the option of actually 4 states, then that will mean by default, if we transition between 4 and 2, of course, the 4 in computation will be a little bit fast. very abstract, may not make sense, but let me just put it in general. An element of the speed, of course, something faster than the classical computers or the usual computers. So we try utilize that. And then if we have very fast speeds, then also the rate at which or the speed at which we'll solve complex problem. I use the case of the DNA sequencing, a little bit deeper, a little bit faster. Then cryptography, quite common, is just a way of securing data or for element of data integrity, confidentiality, or talk of the whole aim of cryptography, this confidentiality, integrity, availability element. So we always use a summary of a CIA option. If you check for quite a number of quantum platforms, a number of them by default actually support different algorithm. There is, for example, algorithm we call an RSA being a public key algorithm. And for most of the time, we'd say in classical computers is quite safe. But just a sure algorithm within, I hope that's the correct pronunciation, SHORS or SHOR is just one of the quantum algorithm which illustrate that the factorization of the public or basically the prime numbers in RSAs can actually be broken using a quantum computer, because with RSA, we always assume if we factor a very large number, it takes time to actually break or actually find those prime numbers. But if you use a super fast computer, quantum computer, then it's actually easy to break that. So that's why the Shor's algorithm explain that. Then with machine learning, so if we talk about advance of it is the quantum machine learning. So the usual we do the models using machine learning. Then with quantum machine learning is we'd want to accelerate AI model training, testing, and of course just the execution of the algorithm itself, of the processing of the algorithm. It may be just a basic with illustration of if I'm trying to break some hashes using CPU and GPU being very fast. So with the concept of the quantum then is adopting maybe more speeds. So that is more of introduction. So what was expected of this session? This being a Fall Fest edition, Strathmore edition, which we calling it IBM or more of Qiskit. So Qiskit is a development environment, or actually the tool used for quantum learning. And with Qiskit has quite a number of features. If we had someone from IBM explain, they'd actually try explain to you from the basics, the free tools, and actually what they consider premium. There is, for those who attended the summer school, most probably I think this bit of explain. And normally, if you use maybe IBM with Qiskit for some time, I think before being ambassador there's quite a number of badges. It's like level 1, level 2, level 3. So if someone is at level 4, level 5, that means the higher the badge mean more features of the tools it actually can use. So which is also just to say, if it's an ambassador program, then of course that person will be considered maybe a better position to recommend Qiskit for that case. But I believe from the IBM perspective will be, if someone have picked badge level 1, level 2, level 3, then there's high chances of them, of course, utilizing the raw tools from IBM, or from Qiskit, not IBM generally. And of course, being ambassador or actually contribute to the developer community of Qiskit. It's most open source tool will work with that, but quantum being a new thing is important, especially for building community. So if it's a Qiskit community, then that means someone at level 5 will actually then contributed much. So of course, just need for access to more features. As I speak here, I'm not speaking as an Qiskit IBM ambassador. That's why I'm just speaking a neutral environment. I'm not one of them. But if we're teaching ourselves from the scratch, or at least speaking from at some point, the most important thing is always, where do I start? So if you've attended the IBM summer school for quantum environment, for quantum computing, then Qiskit is a tool actually you'd know. Then for those who might have joined other communities, another loud tool is, for example, Google Quantum AI. And with Google Quantum AI, there is quite a number of communities. And a common one is something to do with, for example, community on developing quantum noise sort of resistant software, or community dealing with decoherence and quantum noise, which is always a side effect of it. So I may just say there's a few kind of communities with that. So whichever community you are, so maybe might not be, because understand we might be at different level. But if we're picking up from somewhere, of course, we'll always want to explore what environment will be good for us. So this is the case where I'm actually just to start. Maybe up to there. We all at least okay, or at least can hear me somehow clearly. Just in case if I'm moving too fast, I know excitement can also be a little bit high, assumption as well, just coming a lot. Assuming maybe two basics, or just assuming this very new guys interacting with. So let me just confirm, at least we all together have not lost some guys. Can I get maybe a few thumbs up? Okay, that's good. So we can check a few tools we can always explore when dealing with quantum. Again, I've tried to put this to be very general. I'm trying to be also to avoid being very biased with any of the tools, even though, of course, may actually utilize two kind of environment, and maybe I may just want to insist, okay, this and this advantage of this, which is that. So the first option is then, what tools can we always use, or actually you could actually find from there. So I had mentioned, of course, about the IBM, and I put that on the list because this was an IBM Qiskit Fall Festival. So it's just that decided maybe not to really concentrate on it. Okay, thank you, Cyril. So Cyril says, if you have any question, you can just post in the chats, which is very important. So Qiskit is a tool provided, development toolkit provided by IBM. I just put the link there, quantumcloudibm.com, which always required you with a cloud ID. I put something with Amazon there. So as a list, Microsoft Azure Quantum with a link there. So especially for those who prefer utilizing Azure products. Understand, as a university student, especially here, we may be from different universities, or basically maybe organizations which are not educational. But a few education organizations, for example, Strathmore, we use most of the Azure products. So that would mean, as a student, Office 365, at least there is a subscription for that. And if you'd want to, for example, use Azure Cloud Environment options, like deploying a virtual machine, a Docker, Kubernetes, there is always some kind of a free credits before maybe paying for it. So the credits normally is around 100. It's the usual student package. So with that, then, of course, with the quantum, it's always a few credits, and then, of course, the rest, I may not say it's actually more free, unless otherwise if joining from a specific community. Then a very common tool especially if you're doing open source. It may also integrate some tools from different service provider. It's penny-lane, and for most of the cases is I've observed this, especially for the guys doing quantum machine learning. It's quite an easy one, especially if you try and learn, because purely it's an open source Python library. So being a library, it's fine. It's easy for most of my friend picking up with this. And then later on now, provisioning, let's say, a resource or an instance from either Qiskit or from other service providers. So it's always a starting point for it. And the reason is because I said it's open source. Some, of course, of the resources provided by other service provider, it may not be really negligible. So especially if you're a student and with no budget. So it could be a place starting with. Then a common one, if you searching, for example, a course, I think this is easiest always. For example, there is a course in Coursera on quantum. So, however, of course, it comes as a quantum error correction course. But for most of the cases, it's leads you to some resources in Google Quantum AI. So it's more of just dedicated research for focused on quantum computing elements. So a few things, for example, CIRQ, just trying to avoid that because sometimes mispronunciation. For most of such kind of environment, you find actually owned by Google, and it's a platform which I don't want to say it's easy to use, but at times provide that hands-on when trying actually most of these quantum related elements. Two is there is some tools owned by Google like Colab, which at times easy to integrate with this one. So if you think of development environment, especially cloud-based, then it's easily integrated. For example, unlike Penguin, which is purely open source Python, at least with this, then provide that kind of an experience. Then the list continues. This one, QuantumKE, I came across at some point last year. I didn't actually know much because I had a tool called NVIDIA Nano Toolkit, which is for more computer vision. So I was just checking an element to develop just a model for a quantum computer vision, something to do with computer vision. So instead of the classical machine learning algorithm, we're just taking over quantum. And with that NVIDIA Nano, then came across this platform, QuantumKE. In terms of the use, it's actually good with it, but my observation is that at some point, most of the quantum GPUs looks like not owned by them, especially if not using the toolkit itself for some of the actually libraries for that. Then I think for the others, I find quantum braid or Q braid used by a few of my colleagues come across. With personal opinion, of course, may not say not really a fan of it, but of course it's one example or actually one of the other platform. And I think there could be actually quite a number of them. Why do I put this list? Is just to say if we are a starter, or actually if you're a starter, as a developer for developing quantum models, algorithm, or want to learn a bit of quantum by writing a software. So it's always good to maybe at least know what you'd want to achieve, and then of course what platform will be suitable for you. So some comes as open source, some of course you'll have free resources, very limited, and then if you'd want more premium, and I say might not be really premium, but a bit of a test of something close to quantum hardware, then that's actually where the costs come in. And I said it's not really negligible. It's one of the disadvantages. I think also as for myself, it's what I actually feel as a big disadvantage. If you want really to test something. So most of the platforms which may give something tangible, they're not quite free. So anyway, for those prefer maybe IBM option, this is the case where if you'd want to maybe test a bit of the software or a bit, let's just call quantum workload, there is some options for free resources. This one, I wanted to test a basic a model and thought of maybe just using the minimum or a free resource there. So the resources as well, if normally you just want to test something, really not for a long time, any resource come across, it's fine. As I said, of course, some, if you need something free of error or actually with reduced quantum noise, times come with a cost. So users is always believe on bit of try and error option. So just an option with there. For those who've used a Qiskit environment, you'd actually realize at some point with the API in itself is actually just enough when doing the development. NVIDIA QDIA, I picked this as a screenshot. And while picking as a screenshot, is wanted to illustrate the starter kit, even though of course there is a bit of the learning resources for different documentation. At times it's really very important. And the important element of it is if you'd want a resource for specific period of, for say, duration, and two is the kind of, let's say if you want to develop a specific kind of algorithm, at times specific platform, you can actually recommend for specific kind of a scope of an algorithm you can actually develop. So that's why that kind of a scanning would be very important. So with the starter kit, so there's option to do with optimization, something to do with quantum error correction and simulation. Interest for me most of the time when I check with this site for NVIDIA is the quantum GPU for quantum error correction algorithms. So feel like at least if I can do something with quantum GPU, that will always be good. So it's just a documentation here, not login, not maybe just illustrating, but just it from its actually site. Pennylen, it tells you if you developing algorithm in this case. So one, quantum computing, learn universal, of course, quantum mechanical systems from the general quantum mechanics, anything to do with quantum machine learning, quantum chemistry, and a few, then it's actually your way to go. As I said, it's an open source Python library. So for those who most of the time do machine learning, then you actually just be utilizing the library, and it's one of the tool actually times I find it's easy to start with. So continuing is I added this one, and the purpose for me adding this was to illustrate a few things to do with basics of quantum. So especially on the quantum algorithms option there. So if you allow me just a moment, I want to post that URL on the chats. Then while posting is just to say one or two things with a Pennylen and some algorithms there. So just I stop sharing, pause the chat there, and then go back to sharing. Meanwhile, Cyril, how many minutes do we have? Just in case, because now I was working with 8:30 to about an hour, but I'm not sure if still have the same.
No, we can end the session at 9:45.
9:45 there. Okay, I think that's good time.
All right. In the meantime, you guys can drop in your questions in the chat. Yeah, we'll review them throughout the session, or we can review them at the Q&A at the end.
Okay, there's that one. I pasted on the chats. So I'll just share the website you guys have. And purpose of it is just to mention a few things. So for example, if Penny Lane says, this is a foundation course on quantum, is just to learn a bit of what is that quantum core track about. So they use this as a track. Mostly I find it says for good for actually beginning. Remember, it's an open source Python library, which can actually be good for that. So without no particular order, so one element, of course, or at times kind of side effect of any quantum computer is, of course, things to do to handle with quantum errors, so basically quantum noise. So noise is a general term we use to define errors. So some of the elements which actually may create some impairment about the quantum solutions we create. So as a result, just a way to handle those impairment, there's been a little bit approach on actually to reduce those impairment. So for example, you find something under noise quantum theory, it's more of something to represent elements to handle noise or such kind of an errors. So Pennylen anyway give you as a module and a way just to learn a few things. Things to do with distant measures or quantum error correction. For quantum error correction, most platform has that as it is. I had mentioned something to do with Coursera as one doing a beginning level. And with what Coursera provide that is free, it actually says an quantum error correction, even though it starts with definition of actually the quantum, the kind of quantum computers which exist, because there's different kind of an options when we talk about actually the quantum. So the quantumness of it can always take different forms or representation of actually the qubits by itself. So which at times it's just fine, it's easy for that. Anyway, so let's stick for Penny now. So which this track always learning anything. Then 2 is something to do with simulation. How to simulate physical systems in quantum devices. He said, basically, Pennylane is a library, so not really quantum hardware, but at least it's more platform which can give you a feel of that quantum computer actually running as if this was running on quantum. So basic of introduction, fundamentals, quantum mechanics, quantum circuits, circuit building, things like that, the qubits, the gates, and everything. Anyway, these are just the terms to do with quantum. As I said, we're not really teaching quantum, but I feel like if you'd want to start something, then might be important. And I started saying basically, just picking these platforms, which it's good for you to always know. And of course, with whatever you'd want to start with, then it's good at least you do a bit of evaluation. 2 is some have, they're good in specific angle of things. So it's then better is just deciding which you'd want to go. So this Pennylane being open source, then may provide these options. Is for example, you don't know maybe much how to where to start, and maybe just then learn the basics and a few of its actually courses. The good thing with this is before you say you're building, let's say, a quantum algorithm based on machine learning, quantum cryptography, or any of your specification, by then you have actually learned different concepts. This is for someone who wants to learn the different concepts before actually doing deep writing the software for specific elements. So anyway, vectorization algorithm, I had mentioned here this before the show, which basically just illustrates the element of breaking the RSA. And there's much around it. So anyway, let me go to the last item, which is quantum AI. It's in case I make too much assumption, it's always good to correct with that. And then of course, two is based on your experience. It's always good to provide a comment, which I'm just saying, just giving different options with different platforms. But if you've used one maybe for quite some time, I understand there's quite a good answer on that. So it's can always be important. So then come lastly to this one. I was very specific by checking this screenshot, which basically shows the element of actually developing. So quantum AI is that general. I had not picked track based on any community, but if writing basic option, there is the option to do with quantum virtual machine, which you can always develop, test with that. However, before doing that, there is the element of always using the SIQ. Sometimes someone says SIQ, something like that. On basic of installation, how it works to the point of writing an L1. And for most of us, if you are a developer, of course, I may assume you've actually used Google Colab at some point. For quantum, developers at times find them, or at times you may find someone say, I prefer QBraid because of A, B, C, D. So, which is still okay. But if we're learning, picking up from somewhere, I feel this is, apart from the Penny can always be a good place to start with. You've written machine learning models before. So basically, how do we pick up from there? So it's basic using Google Colab. So instead of machine learning is then at least use one or two libraries, which give us a quantum implementation of a few things. So this is the quantum AI. And then of course, the guide as well, if you check on install, it guides you on how to install a few things. So once installed either on Mac, Windows, or Linux, then of course guide you on how to write a bit of the source code and then how to run basically everything in a Colab. Two is as well, if you'd want to integrate to GitHub, which I understand most of us prefer share our work in GitHub, then it's still possible. Anyway, I think most of our work we actually share via GitHub, which is a good thing. So this is the case with the quantum virtual machine. This one I was trying to, as well the same code trying to test on Qiskit is the same load, was trying to work around this one. So at times you find yourself, if you working or basically trying different algorithm, you find yourself running a number of these elements. So anyway, the list will be very long, and the aim of this was basically just to mention one or two of different environments, and also just to mention the aspect of that when we talk about quantum computing, based on the available platforms, most of it you'd actually find we run on a simulated environment. There's also some option of quantum hardware, which I actually say for now it's that expensive. So if you want to test for some, then of course come with a cost. However, of course, with this environment, they still give you the option with quantum. So up to here, then what I understand there should be a bit of a hackathon coming up. And so far, I may pick one or two recommendation. So if you've worked with Collab, then might be actually an easy one to pick. So that's why I just pick. Where would you want to start? We can start with assumption at least you've worked with maybe a machine learning project. If not, I think still okay. At least if done basic of coding, then there's a way to start. If you use Colab, for example. Two, can someone just start with a bit of QBraid? It's still okay. So it's good to explore, at least knowing there's quite a number of platform for that. For now, if no budget, of course, there's always the free platform, which is quite a number of them. So at least to that list, there's a bit of my recommendation. I think that's brief for there. So I would want maybe to welcome comments. So maybe based on observation, based on some work done before, we can always just have a bit of the discussion here. Then if there is any question, that's okay. I'll be glad to answer. And if there is someone who feels they can answer certain question best, still okay.